Hello, welcome to Glycolysis. This is the first of the mini lessons covering the stages of cellular respiration. So I'm actually the first two. I'm going to put glycolysis and the acetyl-CoA step together in one because the acetyl-CoA step is like one slide. So we'll work on that right after glycolysis. So before we get into the stages, just looking at the word glycolysis, it's glyco meaning sugar and lysis meaning to split. So glycolysis or glycolysis is the process of splitting sugar, specifically glucose, which is a C6H12O6. So it's a 6-carbon molecule. And by the end of glycolysis, we will split that one 6-carbon molecule into two 3-carbon molecules that will then progress into the acetyl-CoA step. So with this process of sugar splitting or glycolysis, we're going to be doing some redox reactions. We're going to make a little bit of ATP, those 2 ATPs per glucose we saw on that overview slide. And then we're also going to make some NADHs. So if you remember those, it was part of the electron carrier. We're going to see some redox reactions. I'll point those out as we get there. For all of these processes for cellular respiration, the takeaway is, because there's a lot of details, and I don't want you to stumble over all of the minutia and the details. So usually what I tell all of my students is I want you to know what goes in, what goes out, so that's the reactants and the products, and why. What's the purpose of this process? So I'm going to go through each of these stages, and then I will kind of wrap up each stage with that answer to that what goes in, what goes out, and why. What's the purpose? All right, so let's get started. So in this first slide, I have just an overview, and then we'll go through the steps individually. But glycolysis can be split into two halves. There's 10 steps. The first 5 steps are called the energy investment phase, right here, and splitting of glucose. The second 5 steps are the energy capture phase, where we're actually going to be making some ATP. So the way that I like to explain it or describe it is if you want to make money, right? If you're going to make a ton of money in the stock market, you have to invest first. You have to put in money to make money. So it takes money to make money, right? So it's the same thing with glycolysis. We have to invest a little bit of energy at the beginning, which will get the ball rolling, and then we'll be able to get our ATP payoff a little bit later. So in this first 5 steps, here's our energy investment. We burn 2 ATPs to get the ball rolling, and then here's our split. All right, we're going to take our 6-carbon glucose and turn it into 2 3-carbon molecules called glyceraldehyde 3-phosphate, or abbreviated as G3P. All right, so then if that's the first 5 steps, and then here's our G3Ps, right? They're just going like this, like that. So in this process of G3Ps, we're going to do some redox right here with our NAD plus and NADHs. And then here's our energy payout, right? We get 4 ATPs at the end. But if you remember, we burned 2. So usually what we say is a net yield of 2 ATPs per molecule of glucose. But we also get these high energy electron carriers of NADH. We get 2 of those. All right, so this is the overview. Let's go through the details. And again, you don't need to know the molecular structure. You don't need to know the names of all of these intermediates, but it's worth it to just go through it so you can see the details. Okay, so here's this energy investment phase. So we start off with our glucose, right? So this is our C6H12O6. And if you're to count them all up, you should be able to find all of those atoms in that molecule. Now we have our first investment of ATP with an enzyme. If you'll notice, it's got the ASE enzyme. You don't need to know the names of the enzymes, but hexokinase. We'll be learning in chapter 6, which will be at the end of the term. We had to rearrange that chapter a little bit. A kinase is an enzyme that adds phosphate groups. So a hexokinase is an enzyme that adds phosphate groups to a hexose sugar, which is a 6-carbon sugar in a ring like a hexagon. So I know there's a lot of terms in biology. Sometimes they actually make sense. So here we have an input of 1 molecule of ATP, and so now we have a phosphorylated glucose molecule. Remember, phosphate groups are the PO4 or PO3 minus, depending on which version you have. But that goes all the way back to our chapter 3 functional groups. We've just popped that third phosphate group off of the ATP and hooked that onto the sugar. So that's this transfer of phosphate onto the sugar. Okay, then we do it again. So now we have another input of ATP, and so now we have 2 phosphate groups hooked on to this sugar. We've rearranged the carbons a little bit, so instead of a glucose molecule, it's now called a fructose, but it's still 6 carbons, and it's phosphorylated on 2 sides. Okay, again, another enzyme, ASE. Don't need to know the names of the enzymes, I'm just pointing that out because we learned that in chapter 7. And so when this fructose 1,6-bisphosphate splits, this is the actual splitting part of glucose, it produces one glyceraldehyde 3-phosphate, and it produces another 3-carbon molecule called dihydroxyacetone phosphate. So each 3 carbons gets their own phosphate group, but the next stage only works with glyceraldehyde 3-phosphate. So there's an enzyme called isomerase that will convert any dihydroxyacetone into G3P. So really, by the time we get done with this 5th step, we're going to have 2 of those glyceraldehyde 3-phosphates. So that's what's going to move into the energy reclamation phase. All right, so we've gone through the first 5 steps. This was our energy investment, phosphorylating the glucose, burning a couple ATPs to get those phosphate groups hooked on to those sugars. All right, so now we're at the energy capture phase. So it's not drawing them, but here's our 2 G3Ps, the glyceraldehyde 3-phosphates, and this is our first redox reaction. Okay, so I'm going to draw this out. So let's say we have G3P, okay, on one side of the reaction arrow, plus what's going in, look over here, and this is a double. I'm just showing it for once, but remember there's 2 G3P, so everything that's happening in these rest of these slides, you have to double. So G3P plus NAD plus goes to, this is our 1,3-bisphosphoglycerate, just an abbreviation. Again, you don't need to know that. I'll kind of give you a takeaway, plus NADH. All right, so here's our reaction. We have a G3P, which is a carbon-containing molecule. It came from glucose. And now we have an NAD+. And then the result is another 3-carbon molecule, but that NAD+ got turned into NADH. Now, what did we say got carried along on hydrogen atoms? Electrons, right? So here are some electrons bound to some hydrogens. They're going to go along with the hydrogens to the NAD+. And so that electron's hanging out in this new NADH molecule. You can go back and take a look at the end of the reactions lecture in chapter 7 shows you how that NAD+ gets reduced to NADH. And so this is what's happening. So G3P is being oxidized. NAD+ is being reduced, right? So G3P is losing electrons, so being stripped away. NAD+ is gaining those electrons with that hydrogen. So anytime you see this combination of a reaction, NAD+ going in, NADH going out, that's your clue that it is a redox reaction. We are stripping those electrons away from some carbon-based molecule, in this case it's G3P, storing those electrons temporarily onto the NADH. Now we don't know the reason for that yet. We're going to get there. It's called the electron transport chain. There's a little bit of foreshadowing for you. So these high energy electrons that are now hanging out with this NADH molecule, it's like a bucket. So think of your NAD+ as like an empty electron bucket, and then it gets those electrons from the G3P, puts those electrons in its bucket. It's now NADH, and now it can safely carry those high energy electrons into the mitochondria for the electron transport chain. So when we get there, you'll see where those electrons are going to play their role in the electron transport chain. All right, so we get a little bit of energy in that NADH, but it's not ATP. If you take a look at the next step, here we are at our first production of ATP. So we have another enzyme, right, our ASE ending. We are going to strip some of that phosphate group. This phosphate right here is going to go hook onto the ADP to make ATP, right? Bang, we just got 2 ATPs. And we have now another phosphoglycerate. Okay, the next couple stages, we're just rearranging things. So we're going to take, here's another ASE enzyme. 2,2-phosphoglycerate is going to turn into a phosphoenolpyruvate. Again, you don't need to know these intermediates, but this last step between 9 and 10, this is another energy payoff because we still have a phosphate group. We don't need that hooked on to our carbon. We're going to put that phosphate group onto a couple ADPs, and now we have our 2 ATPs. So that is our energy gathering stage. We got electrons stored in the form of NADH, and we have just made 4 ATPs. But remember, we burned 2 ATPs to get the whole process started. So we've gained 2 NADHs and 2 net ATPs, as well as a couple waters and 2 pyruvates. So this is the 3-carbon molecule that's the end step of glycolysis. It's what comes out in addition to those NADHs and NADHs and ATPs. And the pyruvates are needed to go into the next step of cellular respiration, that acetyl-CoA step, which we'll get to here in a bit. So if we're to look at the summary, so this is that takeaway, what goes in, what goes out, and why. So here's the in, right? So this is what goes in. 1 glucose molecule goes in. 2 ATPs go in because that's our energy investment. 2 NAD pluses go in, and 4 ADPs go in. So these are all the reactants. And what comes out is over here. These are the products. You get 2 net ATPs, you get 2 NADHs, you get 2 pyruvates, and you get a couple waters. And I've listed here on this slide what happens to those products. The ATP is used by the cell, the NADH goes to the electron transport chain, pyruvates go to the next step, and water can just be used by the cell. Okay, that's great, just like the ATP can be used by the cell. Okay, so that's what goes in, what goes out, and the why, that is a really bad why. And that's a different color red. I'll get it one of these times. There we go. And the big why of glycolysis is a couple. There's a couple whys. One, we get ATP, right? We can use glycolysis to directly give us our ATPs. The second why is it allows us to produce the NADH, which we can further make more ATP later on in the electron transport chain. And then lastly, a big why is the pyruvates allow us to do more with those carbons, those 3 carbons in each of the pyruvates. Because if we were done, if that's all we could get out of the glucose was 2 molecules of ATP per glucose, we wouldn't be able to run very many cellular processes. That's not a very big payoff. 1 molecule of glucose gives you 2 molecules of ATP. There's some cells that can live on that. So a lot of bacteria, that's all they get for their ATP. But our cells are more complex. We have higher energy demands. And there's still a lot of energy stored in those pyruvic acid, pyruvates or pyruvic acid molecules. So the pyruvates are setting the stage for further oxidation of those carbon-based molecules so we can harness that energy. So remember our little rock going down the steps? This 10 steps of glycolysis is allowing us to slowly extract the energy from glucose. We don't want a big explosion. We don't want to burn glucose up in a flaming ball of light and heat, but we're getting a little bit at a time. We get a little bit of ATP, we get a little bit of electrons, and we get a little bit of still some energy stored in those covalent bonds of the pyruvic acid. Okay, so that is our glycolysis in summary. This is a video that I have linked to the helpful links. It's a song. It's called the Glycolysis Rap. It's a lot of fun. I can't play it now, but I highly encourage you to go play it. It's subtitled, so he's got the words on it, and it's very scientifically accurate. So if you like a more audible way of learning, music-wise, and it's kind of a catchy little tune, so you might be singing it to yourself, I encourage you to go and watch this glycolysis rap. He has some for Krebs cycle and the electron transport chain as well, but the glycolysis one is my favorite. Okay, so on to that next step. So this is step 2. So phase 2 of cellular respiration. We got through glycolysis. We produced our pyruvic acid. So here's our all those 10 steps, right? They've just minimized into one arrow, but really it's all those 10 steps. So at the end of glycolysis, here's our pyruvic acid. So again, it's a 3-carbon molecule. So we can see 1, 2, 3 carbons. It's an acid, so it's got the COOH. It's one of our functional groups. It's a carboxylic acid. And I've highlighted on the slide here, I've highlighted the carbons and the oxygens and the hydrogens that are going to go into these other reactions. And this is a multi-part reaction. I know it's one step, but it actually has 3 things that are going on. So I'm going to do one thing at a time, and then we'll have our summary slide to wrap it up. So the first thing that's going to happen is we are going to swap out this COOH group here. We're going to swap that for a coenzyme. So these guys are going to change places with a little bit of modification. It's not a straight swapping over, because if we take a look at it over here, our product, we have a coenzyme in the place of that COOH. So we're going to take off the COOH and we're going to hook on the coenzyme. Now, what do we need a coenzyme for? You can go back and look in chapter 7 enzyme lecture. Coenzymes help to make the enzymes work. So it's going to take this acetyl group, this now 2-carbon molecule, with the coenzyme A, is going to allow it to move right into the next catalyst, enzyme catalyzed reaction of the citric acid cycle. All right, so when we swap off that COOH for the coenzyme, it's not, like I said, it's not a straight swap over. The carbon and 2 oxygens are given off. This is called a decarboxylation. That's a long word, decarboxylation reaction. We're removing a carbon dioxide. But if we take a look at it, where'd the H go? Okay, so we have a coenzyme swapping. We have a decarboxylation reaction. And that H, take a look, we have an NAD plus to an NADH. So the electrons that are hanging out with that hydrogen go to the NADH, giving us, or NAD plus giving us NADH. That is another redox reaction. So again, we are stripping some electrons away from the pyruvic acid, storing them in our another electron bucket, right? So we had an NAD plus, it stripped the electrons with the hydrogen, dumped them into the bucket, and now that bucket's going to head off to the electron transport chain. And then our product of the, this is called acetyl-CoA. And so it's going to go into the 3rd phase of cellular respiration called the Krebs cycle. All right, so it's kind of like 3 steps in one. So we get the coenzyme added, we get the decarboxylation produced, and we get the NADH produced. So kind of like 3 products. Now I wanted to talk about this decarboxylation. So we know just from living life as an adult, we should be familiar with this with breathing. We take in oxygen and we exhale carbon dioxide. Well, where does that carbon dioxide come from? It comes from our cells. Well, where inside of our cells does that carbon dioxide come from? It comes from this reaction. This CO2 that's produced by this acetyl-CoA step is the CO2 that your body, your cells are producing that you need to exhale. Isn't that cool? You just learned where that CO2 comes from in the chemical reaction. And where did that carbon originate? Well, it came from the pyruvic acid. Well, where did the pyruvic acid come from? If we go all the way back to the beginning, it came from the glucose. So if you think about it, the food that you eat, the glucose, the proteins, the fats, they all run through these processes. The glucose, because if you remember from that big overall reaction, the glucose gets oxidized into what? Carbon dioxide. And we just saw this a little bit. There were 6 carbons and we're only seeing 2, right? Because we got a double because there's 2 pyruvates. So of the 6 carbons in the glucose, 2 of those are exhaled, 2 of those are made in this acetyl-CoA step that we will then be able to exhale. Okay, and we'll see that again in the Krebs, because the Krebs is where the rest of that carbon dioxide is coming from, that we are breaking down the glucose. So here's our summary slide. of this acetyl-CoA step. So here's what goes in, the per pyruvate. Excuse me. Get some water. So per pyruvate, 1 pyruvate goes in, 1 NAD plus, and 1 CoA. What comes out per pyruvate is we get 1 CO2, 1 NADH, and 1 acetyl-CoA. It's like a 1-to-1 ratio. And what is the why? Okay, so why do we do this acetyl-CoA step? Well, it's going to allow us to further oxidize the carbon molecule, the pyruvate, to get us the NADH. It's going to go to the electron transport chain. And it's going to allow us to make the acetyl-CoA, which is now ready to go into the next step, which is the Krebs cycle or the citric acid cycle. Either one of those terms are fine. All right, so that's what goes in, what goes out, and why. And we learned a little bit about where your carbon dioxide comes from. All right, so that wraps up steps 1 and 2. I will see you next time for the Krebs cycle. Bye.